Ladies and gentlemen, good morning and welcome to another session of the European Research Days. My name is Pietro Caloprisco. I'm a project officer at the Clean Hydrogen Joint Undertaking, and I will be the moderator for this session. This promises to be another very interesting session where we continue with the excursus with an overview of all the projects that are being funded by the joint undertaking. And the specific focus of this panel will be about the building blocks for transport. We have heard yesterday during the overview of all our transport projects, and earlier on in another session that was chaired by my colleague Luca about our exciting, beautiful demonstration projects. We have seen the trucks, we have seen planes flying on hydrogen, boats, ports operations, very many interesting applications. But as you can imagine, this is the end of a trip, the end of a journey, the tip of the iceberg. A journey that starts in our European laboratories, where we are working constantly on the improvement of the components, of the key components which are needed for the transport applications. So the increased lifetime, the increased performance, the decrease of the cost of these components, improving their manufacturability, researching new materials. These are all the challenges that are needed to make sure that we can move from what we've seen in the past, the light duty vehicle applications, to where the market is going. So trucks, planes, and a lot of it. And of course, we will see today with the selection of projects how these challenges are being faced at the low TRL and how not only the traditional KPIs are being addressed, but also how we are more and more trying to adapt these applications, these components for the heavy duty applications. We have a selection of 4 projects, 4 speakers that will guide us through some of the key achievements at program level that we wanted to highlight and discuss with you today. Now, before we move on to this presentation, I want to remind you once again that you are able and you are invited to interact with us. You have the Slido tool that will allow you to put your questions that we will discuss at the end of the 4 presentations. So don't be shy, feel free to ask anything you would like to know that has not been covered by the presentations. Today, in particular, we will focus on the MEA, stacks, and tanks. And we will start immediately with the first project, which is called CAMELOT. And the first speaker will be Patrick Fortin, who's a research scientist at SINTEF. And the project is focusing on the development of the next generation of MEA. And Patrick, I hope you are here with us and ready to get started. We are curious and willing to hear about the project CAMELOT and some of your achievements so far. The floor is yours.
Thanks, Pietro. Good morning, everybody. My name's Patrick. I'm a research scientist at SINTEF, which is a research organization in Norway. And so I'm happy to be here this morning to talk about the CAMELOT project, which is all about understanding charge, mass, and heat transfer in fuel cells for transport applications. So the project started in 2020 and will finish at the end of this year. Total project budget of about 2.3 million euros, as this is a low TRL research and innovation action. This was 100% funded through the Clean Hydrogen Partnership. And we have various partners around Europe. So of course we have got SINTEF coordinating the project, located in Norway. PowerCell Group, these are a Swedish fuel cell manufacturer who've been doing the short stack testing of the components that we've been developing. Technical University of Chemnitz is involved in the modeling out of Germany, as well IMTech at the University of Freiburg are involved in the characterization of the new components that we're developing. BMW has also been involved in the automotive testing. Johnson Matthey, they're our component manufacturer and supplier for the project. Fast Simulations, these are a computational chemistry firm that have really been developing the model and the driving force behind the model that we're developing within the project. And Pretexo is a French company that's in charge of all the communication and dissemination within the project. So looking at the project summary here, the overall goal of this CAMELOT project is to improve the power density of fuel cells by really understanding the performance limitation of the MEAs. And it can really be divided into three main pillars, namely the material development side, the characterization, and then the modeling. And so the first objective of the project is to diagnose fundamental transport properties that limit the performance in state-of-the-art prototype MEAs, and really extending an open source model to enable the accurate simulation of state-of-the-art MEAs using automotive single repeat unit hardware. So that's effectively this first row on this flow chart here, where we received state-of-the-art MEAs from Johnson Matthey. We did a lot of characterization and diagnostics of these materials in order to extract performance metrics and physical parameters that we fed to this model. And then the model gave us the voltage loss breakdown, told us, okay, which components are really contributing to performance in which layers. And that led to an initial understanding of the performance limitations. And then based on these initial understandings, we were able to then go back to the drawing board in the material development column and develop a sort of like a second generation of materials. And then we repeat that process. Again, we test the next generation, we feed the new information to the model, and we come up with more design concepts. And then we have this iterative feedback loop of material development, characterization, and modeling understanding. And then, so this led to the final objective here, proposing new beyond state-of-the-art designs for automotive fuel cell stacks to address state-of-the-art performance limitations. So with that being said, the main target is power density in this project, and not only power density, but achieving power densities at low loadings of platinum group metals. So it's important not only to have good performance, but we also want to look towards reducing cost and the use of these precious metals. So these are quite ambitious. We've reached about 0.75 watts. We're still quite a ways from our target. This is with 0.1 milligrams of platinum at the cathode catalyst. You can see here in the polarization curves, what we've really done is looked at three different iterations of material. So we started off with our baseline catalyst-coated membrane, which was 15, using a membrane that was 15 micrometers thick, and we started with 0.4 milligrams of platinum per centimeter square. And then the first I guess what we call it our intermediate intermediate CCM, we reduced the total platinum loading so that we kept membrane thickness the same, reduce the catalyst loading fourfold, and so you can really get the effect of the influence of platinum loading on performance. And then we kept platinum loading the same at 0.1, and then we reduced the the membrane thickness even further to 10 micrometers thickness in our prototype. And you can see here the performance as we excuse me, as we reduce our catalyst loading from the blue curve down to the red curve, you really see a pretty big hit in our performance here, both in the kinetic region, the ohmic region, and in our mass transport region of the polarization curves. And then we see that as you further reduce membrane thickness, you get a little bit of a reduction in performance. This is interesting for us. We thought that we would actually start to see better performance with reduced membrane thickness. You can imagine there's less ohmic resistance now as you go to a thinner membrane, but we see it's actually quite similar. So this leads us to believe that there is a lot of interfacial effects, that the membrane and bulk transport influences aren't as important anymore. So really, yeah, dominated by things like hydrogen crossover at this point. We have some more data to show that, but yeah, these are all collected under EU harmonized conditions so that we have a sort of like base reference. We could probably get these numbers a little bit higher at a little bit higher relative humidities, but these are all being done at 80 degrees, 50% relative humidity at the anode, 30% relative humidity at the cathode. So these are quite dry, 1.5 and 1.3 bar gauge. And then our stoics are a little bit higher because we use a flow field configuration that is this fivefold parallel serpentine, which has quite a significant pressure drop across the inlet outlet. So some technical information for anyone that's interested there. And so, yeah, power density, we still have quite a ways to go, but I think we have a really good understanding of some of the influence now of the catalyst and membrane thickness on overall performance. The second target of the project was actually implemented graded catalyst layers. So we know that concentration, temperature, and pressure gradients exist during PEM fuel cell operation. If you look at water distribution, for example, here you have a typical flow field configuration, this sort of serpentine pattern. Your water distribution at the cathode, when your air comes into the fuel cell, is quite low. Not a whole lot of water content, but as that oxygen starts getting used up, you're creating water as a byproduct, and so the air picks up a lot of water on its way out, and so you get quite a lot of water content towards the outlet. So we know there's going to be a distribution of water, and I mentioned that oxygen is getting used up as well. So your oxygen concentration is highest at the inlet, and then as you use the oxygen to create water, you decrease your oxygen content. So you can do things like increasing catalyst content in the XY direction, or ionomer content in the XY direction to sort of overcome some of these limitations that are caused by the water distribution. You can also get similar gradients in the Z direction. So you can imagine your membrane is down here, and then your flow field or your GDL is at the top here. So again, you can create ionomer gradients or platinum gradients that are going to sort of overcome these concentration gradients. And so we wanted to see if we could make some graded catalyst layers with our materials, and that's exactly what we did. So at Johnson Matthey, they optimized these printing for gradient layers. So they made these catalyst coated membranes now at large enough scale for automotive fuel cell stacks. So these are about 300 square centimeter active area CCMs. And you can see here, these are X-ray. This is a sort of overlay of an X-ray fluorescence spectrogram. And you can see where we have a total loading that's quite low at 0.1, but you have a nice gradient as you go from left to right, where you have high loadings on the left down to lower loadings on the right. And then so we wanted to put them into a automotive stack over a power cell, and we have a current distribution plate, which is quite neat, where you can actually see the current distribution over the entire width of the cell. You can see it's about 10 centimeters by 30 centimeters, like I said, about 300 square centimeters active area. And you can see when you plot this in 3D, you have high current density towards the inlet. Right? So the air inlet is on the left-hand side, and then towards the outlet, you get low concentration or low current density. And that's again because of this lack of oxygen and increased water that we talked about. So you get this current density. So what we did, we actually, in order to try to homogenize this current density distribution, we put this graded CCM in where we had high loadings towards the outlet and low loadings towards the inlet. And you can see that now when you increase the concentration of your catalyst, you can actually utilize that low concentration of oxygen a little bit better. So this is great for homogenizing current density distribution, but at the same time, it's not the most optimum use of oxygen. Right? In theory, you'd like to utilize more oxygen where it's more prevalent. So your performance, if we look here, so the previous generation, this homogeneous catalyst layer on top here, that is both the orange and this dashed line are repeat measurements of that. And the green line down here that shows a little bit worse performance is when you have high loadings towards the outlet and low loadings towards the inlet. It's basically just non-optimal use of where your concentration gradients are higher, but you see this increase in the mass transport. You basically limit your mass transport issues towards the outlet because now you can use those low, you have more access to those lower oxygen concentrations. So it's a bit of a trade-off. And so these are quite recent results. The next step is to do another test where we switch it. Now we have high loadings where we're probably going to end up with a much sharper distribution of our current densities, but we're going to get higher power density. So then it's a question of what is the trade-off here between current density homogenization versus optimal power density. Yeah, so that interesting results. So what did we learn from this? So the main takeaway here is that as you approach these ultra low catalyst loadings towards 0.08 megs of platinum per centimeter square, you start seeing significant both kinetic and mass transport limitations that have to be overcome. Kinetics, there's a lot of good work that's being done through the development of new oxygen reduction reaction catalysts with high mass activities. You can look at shape control platinum alloys or even these PGM-free so-called MNC materials are getting a lot of hype right now. So there's two really nice reviews that have recently come out. One by Peter Strasser and co, and another one by Dustin Banham, both excellent, world-class catalyst researchers. So I'll leave these here. You can go take a look at some of the new catalysts that are being developed, but also mass transport limitations. And this is really a little bit trickier. This has to come through catalyst layer structure and morphology engineering. So like we talked a little bit about these graded catalyst layers, but also looking at the materials properties themselves, the carbon support optimization of the ionomer, maximizing triple phase boundary. So a lot of it comes down through engineering the morphology of the catalyst layer. Yeah. So a lot still that has to be overcome, but there's a lot of good research out there that's working towards these goals. In terms of exploitation and impact, so just for the sake of time, I haven't been able to talk about it much, but we've actually developed an open source 3D model that is used to predict the performance of these PEMFCs. So there's equations for each of these physical parameters and processes that happen at the fuel cell, and they're combined into this really complicated PEMFC comprehensive PEM fuel cell model that takes a look at all these different phenomena at different locations in the fuel cell. And we've been highlighted on the EU Innovation Radar here. That's all done by fast simulations. And so this is a really useful tool from everyone from graduate students through research directors who are trying to develop new catalyst layers. You can really use this tool and take a look at, okay, if we change this parameter in our process, how does that going to influence the performance of the fuel cell and the polarization curve? So it's quite nice. And so, yeah, you quantify and predict local operating conditions inside the MEA, and as well as looking at the MEA as a whole and component-based design recommendations for increased performance. And we're actually hosting a workshop in Chemnitz in the first week of December 6th and 7th. That's going to be all about the model. So it's a free workshop. If you're interested at all in learning more about the model and how to use the model, come through to Chemnitz. You can visit the website here, camelotfuelcell.eu, register for it completely free. And we're going to give you like a hands-on demonstration, the guys at FastFC, David and Yuri, how to use it, troubleshoot it, any questions you might have. We're also going to have a booth at the EU Project Pavilion in Brussels next week. So come by, say hi. Yeah, I'm happy to meet all you guys and talk a little bit more about PEM fuel cells. Thank you to Clean Hydrogen Partnership for the funding, and thank you all for your attention. Happy to answer any questions at the end.
Thank you. Thank you very much, Patrick, for this very interesting presentation. It's fascinating to see how in depth you went with your assessment, also to produce this model, and how much knowledge you have already produced on the way to achieve the targets you're seeking. So thank you very much, and we will take a question that we will address them then later at the end of the session. But now I would like then to invite the next speaker to join us. He is Joël Pauchet. He is a senior expert and project manager at the CEA, and he will be here talking us about the project DOLPHIN, which is dealing with the PEM fuel cell stack technologies. And the goal, I understand, is indeed, again, to improve the performance, the durability, while reducing the production cost. So Joël, thank you very much for joining us, and please walk us through the achievements of the DOLPHIN project.
Thank you very much, Pietro, for this kind introduction and also for the invitation, of course. Can you see my screen and hear me clearly?
Yes.
Okay. So yes, I will give you a brief overview of DOLPHIN project. So this project is part of the call 2018, and especially dealing with game changer for full set stack for automotive applications. So the project has started beginning of January 2019 and will end at the end of this year. So here you see the values for the funding, and we are roughly close, very close to the end of the project. So this is why I put 95% of completion. You will see what is remaining in coming slides. So in the project, we will have 7 partners, 4 industries and 3 research and technological organizations. In terms of industry, we have Chemus, who supplies us with membrane and ionomer. Symbio in France, who supplies us with requirements for automotive applications, especially for the stack and the system aspect, and also metallic-based solutions and processes. DMG Mori in Germany, specialist of additive manufacturing, and Excel in Austria and France, specialist of carbon-based solutions and processes. All of them contributing to material development. And in terms of RTO, we do have graphene coating analyzed by Manchester University in Great Britain, ZSW in Germany, who helps us in modeling, laser milling, cell and stack tests, and as a final partner, CA, so is coordinating the project and also involved in modeling, printing, and cell and stack tests. So what are the main objectives of the project? Really, the aim is to validate that we can apply to the current stack some disruptive technologies suitable for 100 kilowatt lightweight stacks for automotive applications, and also compatible to large scale mass production. So here you see the table of the KPIs as defined in the call by FCHG at that time, in terms of kilowatt per kilogram, kilowatt per liter, watt per centimeter square, cost, durability, and operating temperature. And here you see the targets that have been defined in the call, targets aiming at reaching them in 2024. So we see the targets we will try and reach in the frame of the DOLPHIN project. So 4 kilowatt per kilogram, 5 kilowatt per liter, 2 watts per centimeter square, less than 20 euros per kilowatt, and 6,000 hours and 105 degrees C. And as a reference, we have taken the AutoStack Core project, which is also a European-funded project. And here in 2017, when we started to think about the DOLPHIN project, AutoStack Core Evolution 2 was one of the best of the world. So this is why we have taken this as a reference. And you see that for each KPIs already reached by AutoStack Core at that time, the targets correspond to a large increase in terms of each of these KPIs, especially dealing with the power density, which is nearly to double the power density compared to AutoStack Core. And the result is that what we do want to do in the frame of the DOLPHIN project, which is 2 watt per centimeter square target, is to move from the polarization curve, from this blue-green curve, which is the one of AutoStack, to this red one, which is which will allow us to reach this 2 watt per centimeter square target at 3 amps per centimeter square. So here are the global objectives. How shall we do that? At the end of the project, this is ongoing now. So we are assembling, and we will test 2 stacks, which we can call demonstrator stacks of around 5 kilowatt. One tested, assembled and tested at CA, and the other one at SW. And each of them will include part of these innovative techniques we have developed in the project. For instance, we are working on the terminal plate that Excel has helped us to define, design, and manufacture. It is a carbon-based terminal plate. We have also worked on the MEA and on the flow fields. For instance, on the flow fields, we have developed techniques in order to reduce the thickness of the metallic plate, and also we have worked on carbon-based plates. We have also spent a lot of time to reduce to downsize the rib channel pitch by different techniques, either by printing, molding, stamping, additive manufacturing, and also laser milling. And all these combine also, of course, the effort of different partners. We have worked on the gas diffusion layer, either to try and thin the gas diffusion layer or remove one gas diffusion substrate from of one side. And here, dealing with the MEA, we have worked with improved materials supplied by CHEMOS and also improved ink formulation and processes developed by ourselves in CA. So we will try and combine all these in these two demonstrators. So the first topic of interest is the flow field downsizing. So here you have a sketch of the rib channel pitch, typically. And so we started from a pitch which is typical of autostacos, 1.2 millimeter pitch, and we reduced the dimensions down to 400, 400, 200, 200, and 100, 100. And we tested this on differential cell in order to test the influence of such decrease of pitch depending on the operating condition that happens in a real stack between inlet, middle, and outlet, for instance. And that for two stack operating conditions, low power and max power. And here you see the graph showing the power density in terms of watt per centimeter square, depending on the location in the stack, and for the different rib channel pitches. In black, the classical one, and blue, green, and blue, the reduced dimensions. And you see that whatever the operating conditions are, then we increase drastically the power density by reducing the rib channel pitch. Nevertheless, there is a limit, because when you reduce too much this rib channel pitch, around 100 micrometer, then you have a huge increase of pressure drop, which is detrimental for the system aspect. So we won't go down to 100, but we'll stick to these two values, 400, 400, and 200, 200 micrometers. We also check that it makes also sense with a larger scale. So here you have a single cell of 100 centimeters square, and in which we compare the classical design, 1.2 millimeter pitch, and the reduced ones, and especially the green one, which is close to 200, 200, shows an increase of performance thanks to the rib size downsizing. So clearly there is interest of reducing the pitch, reducing the rib channel dimensions, not too far, but there is an interest. So this will be introduced in the final stacks. And now other developments deal with how can we manufacture such thin flow fields. So again, we started from AutoStack, which is made of stamped metallic bipolar plate, typically 75 micrometer thick, with a rib channel pitch of 1.2 millimeter. And our current situation now is that we can work with plates of a thickness around between 25 and 50 micrometer, and a pitch between 0.6 and 0.8. We could most probably go below, but that would need additional efforts. So what we introduce in the tags are the following developments. First, additive manufacturing. Here you see a sketch of additive manufactured as done by DMG Mori with this kind of thin pitch. So 200 reeds, 400 channel reeds, and 300 micrometer the depth. Maybe we could go below these dimensions, but this should be checked. But one other thing to be reduced is that the weight and the manufacturing time for such plate is quite large. So there is improvements to do in terms of processability. We also develop printing techniques onto metallic and carbon sheets. So here you see an example of what has been done at CA, in which we can print channels and ribs onto metallic or carbon plates. So we have done this also with the dimensions around 400, 500, 200 micrometers. We could most probably go down to smaller dimensions, which seems realistic, but that would need more effort. And also what has been introduced in the stacks is flow field machining in GDL. Here you see an example of with the same design of a GDL mechanical machine in order to manufacture the channels here. The drawback is that it is quite difficult to handle such material, so improvements also shall be done for that. We also worked a little bit with Sambio on the thin metallic sheets stamping, which do not really seem realistic below 800 micrometer pitch with very thin material. So this has not been introduced in the stacks. The two other developments we have introduced also dealing with electrochemical core and terminal plate. So AutoStack based on commercial MEA, commercial CCM, metallic terminal plates and GDL on both sides. So now we have reduced the terminal plate weight. We can remove one GDM on one side, and we have also improved the catalyst layer performance. What has been introduced? First, we developed based on CMOS membrane and ionomer, and also improved ink manufacturing process and formulation at CA. We have improved the performance of the CCL. So here you see a commercial CCL under different operating conditions in a continuous line, and these ones for the DOLPHIN CCM developed by CA with CMOS material. So this is quite interesting, and this has been introduced in the stacks. We have also seen that we can remove a GDL from one side. Here you see the sketch showing the for different operating conditions of the stack. So in black, you have the classical way to assemble with one GDL on cathode side and another one on the anode side. In red, well, you remove the two GDL. In blue, you remove a GDL on one side, keeping only an MPL, and then you keep the GL on the other side, either on the anode or cathode side, blue and green. So you see that if you remove one fiber substrate on one side, keeping only an MPL on one side, you can reach nearly the same performance, whatever the operating condition is, compared to the classical way to assemble with two GDL. So that means that we can save some weight, some manipulation, and also some thickness by removing one component of the assembly. And the last thing is that we developed also with support of Excel some carbon-based terminal plate, which allows to reduce the weight by around, compared to aluminum, around 43%, roughly. What we did not introduce, because we had some first results of interest, but more work will be necessary, is single layer coating on the membranes to reduce the crossover, and also the 3D CCL as described in the previous presentation. This could make sense, but nevertheless, this would need more effort to have a very interesting conclusion. So we have not introduced that in the stacks. So what is the situation now in terms of performance? So again, we started from AutoStack core, a little bit less than 1 watt per centimeter square at 0.66 volts. And then we introduced in a 6-cell stack, each cell of 100 centimeters square, a DOLPHIN CCM made of membrane and ionomer from CMOS, ink formulation and CCM process by CA, combined with thin flow field, defined based on the test of CA, and manufactured by additive manufacturing, followed by DMG Mori and ZSW, and also the manufacture and the test of the stack at ZSW. So this is a 6-cell stack. And we reached quite interesting performance. We have not reached the 2 watts, sorry for that, but we have clearly increased the performance. So up to 1.66 watt per centimeter square, or even more, 1.86 watts at 3 amps per centimeter square. So here you see the improvements in terms of polarization curve. So the reference materials and the improvements. So here the final ones show under the AutoStack core condition, an increase of performance from 1 to 1.2 watts, and at 0.6 watt, 1.465 watts. And even more, if we use the Gaia conditions, which are the conditions sweetly shared with us by the Gaia project, with a little bit higher pressure and stoichiometry, then we can even more increase this performance, up to 1.86 watt per centimeter square at 3 amps per centimeter square. So this is really of interest. So what the perspectives in the coming months is, first we are assembling the two 5 kilowatt stacks, one at ZW, large surface, and another one smaller surface at CA to test performance and durability. Both of them will have the DOLPHIN CCM, and the difference will be dealing with the flow fields. For the ZSW test, it will be done by additive manufacturing with no fiber substrate on one side and using the component template of Excel. And for this, we are seeking for quite high power density, between 1.8 and 1.9 watts per centimeter square. The second one is using the same CCM, but we use the machine flow field in GDL and printing combined with printing approach for the inlet and outlet of the cell. And for this, we expect lower power density, mainly due to the thickness of the rib channel sizes, but we expect having a very high mass and volumic power density, maybe even higher than the targets. We will also update the LCA, showing that we should normally be not so far to the 20 euros per kilowatt. And as a summary, if we come back to the KPIs, so we expect with these stacks to reach between 4.4 and 5 kilowatt per kilogram, around 5 per liter, 1.8, 1.9 watt per centimeter square. Cost should not be very far from the target, and we need to check the durability. And for the increase of temperature, we have some solutions with different membranes and ionomers and formulations, but unfortunately, we could not apply these to the stacks due to material supply. For information, if you compare that to the current status for the auto stack industry situation, which is now also one base state of the art in Europe, they are still a little bit below these targets. So especially for the 1.3 watt per centimeter square, but they have demonstrated that with a real stack that we have not done for DOLPHIN. So we are not very far. We should not be very far from the final state of the art situation with the developments of the project. So no big issue, except that we had, as many people, the pandemic effect that has led to a project extension and also extra costs for the project. Main lessons learned. First, it seemed really realistic to reach the 2024 KPIs as defined by FCHGU at that time. So some solutions appear clearer, and some of them seem really of interest for the future. Another outcome is that we really need to take care when we compare stack performances, because as you know, the operating conditions might be different, etc. And especially there is a trade-off between system and stack performance that is very important to have in mind, and that really has a big influence on the figures we show in terms of stack performance. We have also identified some challenges. The first one is to still improve the processes to manufacture even thinner flow fields. So we have ideas, but extra effort is necessary. It would be also very interesting to combine improvements of different European projects, which is not always obvious due to confidentialities. And so we should be very close, or even higher, or even a little bit lower to the KPIs, but clearly with two stacks using two different technologies. So one challenge should be to combine all these technologies in a single stack. We have already discussed our exploitation plan, which is based on the pathways we have defined to improve stack performance by manufacturing technologies to reduce the weight, the volume, and increase the power density, and to reduce the number of components. And in terms of impact, which this could contribute to increase the KPIs by introducing some DOLPHIN developments in future stacks with potential technological transfers. But what would be really of major interest is to follow up some developments in order to keep improving these developments, because this really makes sense in the future. we have different communication dissemination activities, and especially there is a final, we have already organized a workshop for the project, two workshops in project, one online and one at the ZW premises in 2023. And next year, we will organize a final workshop. So most of you will maybe receive an invitation. And we have also different synergies with different projects. So Gaia, again, thank you for sharing these operating conditions, and also thank you to Autostack Industry for sharing also information we could compare to. That was really helpful. Thank you very much for your attention.
Dear Joel, thank you very much for this very interesting presentation, for showing clearly how many challenges, how many things can still be improved when you open the stack and you really go at the level of the subcomponents. And it was also interesting what you highlighted, how tricky it will be to manufacture some of these components, like the bipolar plates with this level of thickness that needs to be extremely precise. This is indeed one of the challenges that we constantly face. So improving these components and then ensure that the manufacturability can also follow through. Because when we see at the amount that is needed of these components to ensure there are enough trucks and cars in so that we can really contribute to the decarbonization, we are going to very staggering numbers. And we also have to ensure the reliability of all of these components. So this is not a trivial challenge. So thank you very much. Hopefully you will get also some other questions to answer later on during the Q&A session. Now, we leave MEA and stack for a while, and we focus on the tanks, which are facing also quite a few challenges if we want to improve them, and especially at the level of the materials. And we have today here the project Shaped. I'm not entirely sure how to pronounce that. And we have Mr. Eric Deparis, who is the hydrogen storage chief engineer at Plastic Omnium, that will explain us a little bit about the challenges of this additional extremely important component for the fuel cells mobility. Thank you very much, Eric. Please, the floor is yours. I'm afraid, Eric, you are on mute.
I'm sorry for that.
That's good now. Perfect, thank you.
Okay, sorry for that. So hello, everybody. Thank you very much. So the SHAPE project is a project funded by Horizon 2020, and that's a project that includes 4 partners: OMB Saleri in Italy, Ulster University in Ireland, Bundesanstalt für Materialforschung und Prüfung in Germany, and Plastic Omnium New Energies in Belgium. And the challenge of this SHAPE project is about the physical laws, in fact. If you look at the top left picture, you have the ideal shape for a nitrogen storage at high pressure, which is a sphere. If you look at the top right picture, we have the ideal shape and location for a battery pack. A battery pack is EV, so it should be in the bottom side of the car, and it's pretty flat to be under the body of the car. And so combine these two shapes that are absolutely different is very difficult, and that's the target of the SHAPE project, meaning proposing to the industry, an automotive industry, a flat storage, including high pressure vessel of hydrogen. So such a project includes some challenges. So first of all, we are talking about 70 MPa for the pressure. We target also a certain range for the car, meaning 6 kilograms of hydrogen embedded into the car. in a very flat storage. 150 is the initial dimension that we consider for this project. The project is addressing the technical, the safety, performance at different level, at vehicle level, that means system level for us, but also at modular system level. You will see what a module is just after, and at vessel level, the unique cylinder of hydrogen. The third thing is that such a system includes more components, includes more vessels, so reach the target of what euro per kilogram was defined at the beginning of the project. And finally, one of the target is also to contribute to the safety and type approval standards, including the GTR 30. It's a funded project, started in year 20, and it's a 3 years project funded with 1.99, so 2 million euros. What challenges? On safety viewpoint, some specific challenges appear with such a shape. The fire behavior of the system is really the main problem that we are tackling. The second issue will be the hydrogen leakage because of the multiplicity of components, piping, vessels, connections, valves, and last but not least, the hydrogen permeation level, because in such a shape, the ratio between the surface of the envelope and the internal volume is high, and so meaning more permeation for the system. For also such a system, we have to develop manifolds to perform the connection between all the cylinders, and this is one technical challenge that we have addressed with one of the partners. Weight and costs are, I would say, in the same way. More you have components, more you have weight, assembly, and finally cost. So that's the challenges that we have in front of us. And in terms of regulation, we are talking about the new version of the R134 or GTR 30. So the project has been split in several work packages: design of vessel, design valve and components, design the assembly, but also perform some numerical studies to address the fire behavior, prototyping and testing at the end. So let's look at this work package. The first one is the fire behavior, and the consortium addressed the first issue with the fire behavior, because between regulation and real situation, fire situation on the road, we can have a big difference. And the big difference is in the heat release rate on A. So HNR on A means heat release rate on a specific surface. For a spillover of gasoline, like you can see here, the heat release rate on A is 1 megawatt per square meter. And if we look at the results of plenty of studies made by different people all over the world, and if we look at propane or methane fires, all these fires are recommended by GTR 13 regulation are below an HRR on A of 1 megawatt per square meter. If you look at spillover of gasoline, this arrow here, this is propane, but this is spillover of gasoline, then you have an HNR on A, and so that means an heat release rate which is really higher. So this is a concern. What heat release rate for the same temperature, what heat release rate to use to address all safety situations. This study has been made by Ulster University, and you can see some simulations in this slide, some simulations for different heat release rate. Here we have a heat release rate at 0.2 megawatt per square meter, and you can see a small flame going out of the car body up to this point roughly. I don't know if it's very visible, but I hope that the speed of the network allows you to see the flames. For an heat release rate of 1 megawatt, for 1 megawatt per square meter, you see a large flame, large flame going up to the roof of the car. That's a big difference. If we consider the shape storage, meaning all the vessels under the car body, and if we consider also this situation for the vehicle, with a fire condition again, so fire conditions driven by a spillover of gasoline, not hydrogen, but gasoline from another car. So then we can reach high temperature and including an air release. So that's these conditions that we would like also to address during the project. Two conditions can appear in an accident. The first situation could be here with unignited jet. And so in this case, what is important is the flammability limit of the gas. You have here a cloud of gas in a sailing, so in a parking. It's in a parking in Brussels that has been modelized. And you see here in blue the cloud of hydrogen having a concentration above 4%, with an opening for this TPRD, so thermal pressure relief device, that safety device that we have on the storage. The opening of the TPRD is 2 millimeters only. And you see that we have a large cloud of potentially explosive area of explosion. If we reduce the size of the opening here, you see that we have a small area behind and under the car that is at a concentration over 4% of hydrogen, meaning that it's safer. And this is a good recommendation for the design of the storage system to reduce the TPRD orifice diameter in order to reduce the risk of explosion in a parking situation. The second set of pictures is what's happened if we have a fire condition. So the simulation here is showing you what will happen if we have an ignited jet of hydrogen with an orifice of 2 millimeters. And we consider in orange the temperature of 300 degrees, which is the maximum acceptable temperature for the ventilation of the parking. With 0.5 millimeter here, you see that this orange zone doesn't touch the ceiling of the parking, meaning safe condition with a venting system continuing to extract heat and gases. So this is for the numerical simulations done during the project. Regarding the vessel itself, so it's a very strange shape. It's like tubes like that. Diameter is 140 millimeter, length is 1,400 millimeter, 300 millimeter. Well, it's a standard design, but in fact, it's not really a standard design. We had to tackle specific challenges and to reach the, due to the shape and due to the small difference of diameter between the cylindrical section and the boss section. And finally, we reached a target of 5% in terms of gravimetric ratio on these vessels, which is not at the target we expected, but struggling with this small difference of diameter. So the vessel being made, we have also to define the system. And this is what OMB is doing with generation of new components that we decided to create 3 different modules. One module, which is a fueling section, one module, which is a passive section. We can have as many passive sections as we want, and a defueling section, including reduction of pressure and some other safety device for filling of the fuel cell. So we have here the size of one manifold and the representation of all the piping between the manifolds. This is for the gas component, and for the packaging, obviously we have a packaging all over the vessels and the components. And this packaging has been chosen as being aluminum alloy sheet, 1.5 millimeter. And this is a pre-design that that you have in front of you. It's not the final design, but this storage at the end has a size of 1,500 millimeter by 1,700 by 173. So we increase a little bit the size of the shape versus the initial specification for some technical reasons. That's what is ongoing and ongoing to be ready for fire test. Mainly, so BAM in Germany has prepared a specific installation for allowing to have an engulfing fire for such a shape. And you see that it's a very original design with concrete blocks, but also metallic blocks allowing the venting, the gas escape, and allowing to resist in case of burst of the system. This is all the validations that we will perform, not only fire test, but also slow burst, hydraulic test, permeation test, and some drop test at system level. So the testing phase is late. The project is late today. We were struggling with the delivery of the components, and now we arrive in the winter time, which is not the best time for fire test because the conditions, the weather condition, will affect the test, and so we are asking for pushing this testing phase in 2024. So, in a nutshell, 4 partners, funded project, 4 main objectives, and the current status is prototyping. Prototypes are almost finished. They will be delivered this year, and the testing phase will start really in 24 with the fire test in order to provide a good demonstration of this of such a system. Then this is what I can tell you for the SHAPE project, and I'm ready to answer to your questions. Thank you very much.
Yeah, Eric, thank you very much for this very interesting presentation. It was very fascinating to see this innovative design, and also reassuring to see how much efforts you're putting in ensuring the safety of this innovative storage solution. So also for you, I will ask you to please wait and a little bit for the questions after all the presentations, so we can have a bit of a Q&A session. And I would like now to invite for the next presentation, the IMMORTAL project. And in particular, it will be Deborah Jones, who's the research director at the CNRS, that will be delivering this presentation, which is looking at how to improve the durability of the MEA for the specifically heavy-duty applications. Now, before Deborah, I give you the floor, I just wanted to remind the audience once again that you have the possibility to interact with the speakers and put your questions. Next to the box where you see the live streaming, there is like a few dotted colored dots where the name of the session. You simply click on that, and then you can put your questions. Alternatively, you can also search on Google Slido, European Hydrogen Research, or no, actually Slido, and then clean hydrogen, and you should be able to land on the page where you can put your questions. So with that said, Deborah, thank you for your patience, and the floor is yours.
Thank you very much, Pietro, and good morning or good afternoon, everybody. So it's my pleasure to give you an update on the IMMORTAL project. IMMORTAL for improved lifetime stacks for heavy-duty trucks through ultra-durable components. My name is Deborah Jones, and I'm a research director at the CNRS Institute for Molecular Chemistry and Materials Chemistry in Montpellier in France. So let me first of all give you an overview of the project. Project partners are ourselves, CNRS, and we're a research organization. The other research partner in the project is IMTech at the University of Freiburg. The other partners are industrial partners, Johnson Matthey, Bosch, FPT Industrial, AVL, and the small company Protexo, who takes care of communication on the project. The total budget of the project, which is also the European contribution, is almost 4 million. We responded to the call 1.2, durability lifetime of stacks for heavy-duty trucks in 2020. The project started in January of 2021 and has been running then for almost 3 years. So heavy-duty transport application requires high efficiency and durability, and differently from the other projects that we've been involved in collectively with some of our other partners in the past, the IMMORTAL performance target was lower than these recent automotive projects, such as, for example, Inspire Volumetric and Gaia, as Joël was just mentioning, the result from Gaia. So the performance target in IMMORTAL 1.2 watts per square centimeter, but at a higher cell voltage. So Inspire Volumetric Gaia, the nominal cell voltage was 0.6, and the aim there was to achieve 1.5, 1.8 watts per square centimeter. Here in IMMORTAL, 0.675 volts, 1.2 watts per square centimeter. But as we can see from the polarization curve on the left-hand side, that is actually beyond the state of the art compared with, for example, the polarization curve that's given there, which is a result from the Inspire project in a stack. So the beginning of life performance for IMMORTAL, the target, is that green dot there. And also because we're talking about heavy-duty trucks, the lifetime requirement is that much longer, of course, than automotive. The target is 30,000 hours of lifetime, lifetime being defined as a loss of 10% voltage decay. So that would bring us down here to 0.608 volts. So that's the empty triangle that's given there. So over the period of 30,000 hours, between 0.675 volts and 0.608 volts, then actually gives a very low degradation rate, and in fact a degradation rate of only 2 microvolts per hour. So this is the kind of structure of the project in these 5 different blocks. So on the one hand, it was necessary to develop load profile tests specific for heavy-duty membrane electrode assemblies. Everything that had been done in the past, everything that's available was available for automotive. So we needed these LPTs for the MEAs with regard to, in particular, the durability assessment. We needed, as part of the project, of course, to develop durable components and high durability MEAs specifically for heavy-duty truck application, then to validate them using the accelerated stress test and load profile test protocols that we would have developed initially. From the results of those ASTs and LPTs on the membrane electrode assemblies from the project, tested on single cells and on short stacks, use those results to develop an algorithm for lifetime prediction over the 30,000 hours of operation, and ultimately then try to satisfy the project targets in terms of the performance and stack cost. So the TRL at the beginning of the project was 2 to 3. And at the end of the project, the aim then is for TRL 4 to 5, and then the various points that you can see along the line here during the project lifetime are the various milestones. So having developed an initial realistic heavy-duty truck protocol, improve that during the course of time. Initial end-of-test analysis on baseline MEAs, develop durable components, including membranes, catalyst layers, develop the prediction method, and then finally the performance and durability. So let me give you an update on where we are. So the first result in terms of the development of durable materials, then the focus here is on the development of a durable membrane, reinforced membrane. The starting point at the beginning of the project, which was input from Gaia, that we developed at that point a reinforced, nanofiber reinforced 15 micron membrane that had withstood 90,000 accelerated stress test cycles. I'll come back to that in a minute. And during the course of IMMORTAL, we've been able to improve that with now a nanofiber reinforced membrane of 10 micron thickness and withstanding 120,000 of those AST cycles. And in fact, to end of test, because even at the end of these 120,000 AST cycles, there is no mechanical failure, there's no rupture failure. So that result is expressed in the diagram on the bottom left-hand side. This is how we've shown the results in the past. So the bottom of those, the bottom two lines in this graph expresses the differential open circuit voltage with a small overpressure on the anode side. And the top two lines are the OCV value. Here we are doing relative humidity cycling, so fully wet, fully dry, while also holding the cell at open circuit voltage, and the cell temperature is 90 degrees. What you can see on there in the black line is a reference 10 micron membrane with a standard expanded PTFE reinforcement, and the light blue line uses the same MEA construction. It uses the same ionomer, and the difference then is the presence of the latest generation of PBI type nanofiber reinforcement. So when there is a sharp upturn in the differential OCV here, this indicates the beginning of a perforation in the membrane. So that occurred in the reference after 55,000 or so cycles. And then, as I said, this test was stopped here at 120,000 cycles, which actually corresponds to around 2,100 hours of accelerated stress testing. And this surpassed the previous generations of reference membranes and also nanofiber reinforced membranes that we've prepared. So this is on a scaled up membrane. This is part of a 20 linear meter or so roll of these 10 micron reinforced membranes. And this is the membrane that's been used in 2 of the generations of the short stacks that have been prepared and tested. So moving on to the MEAs, and just to take you through this, our baseline membrane, our baseline MEA at the beginning of the project had a total platinum loading of 0.68 milligrams of platinum per square centimeter, at 0.675 volts. Under operation conditions, we were obtaining 1.2 amps per square centimeter. Present stage of the project, we've been able to largely thrift the amount of platinum that is being used, in particular at the cathode of those MEAs, and you can see also that we have achieved an increase in the performance of the MEAs. So I think we can see this nicely on this diagram at the bottom. Here we have our 1.2 watts per square centimeter squared target. The power density during the course of the project increased from the baseline up to Gen 1 and Gen 2, while the platinum loading in terms of the grams of platinum per kilowatt has largely increased, in fact, been divided by 2 over the course of the project, so that's important. So reducing the platinum loading per kilowatt by 60%, we've obtained a beginning of life performance of 0.642 volts at 1.77 amps per square centimeter, which is within 5% of the target. In fact, the target performance for this particular call of 2020 was a little bit higher than the 2024 SRIA targets. So the IMMORTAL MEAs do actually achieve the SRIA 2024 target for heavy-duty vehicles by achieving the 1.2 watts per square centimeter at 0.65 volts. Which is the target then for 2024 in the strategic research agenda. and with 0.36 milligrams of platinum per square centimeter. So let's move on to the other aspects, and I mentioned the load profile test development. So this was done by collaboration between all the partners, but particularly work at FPT Industrial, by work at Bosch, and with contribution from IMTech, University of Freiburg. So initially, a lot of work done on developing or on determining the acceleration factor between what happens, the degradation that occurs on using accelerated stress testing in single cells, and then load profile testing in single cells, and then a scaling factor by load profile testing on short stacks, and scale factor as well by doing the same ASTs on short stacks. So that allowed us to determine an acceleration factor between the AST and the LPT. Now that we had an initial load profile, there was nothing available, let's say, publicly available on load profile testing for short stacks relevant to heavy duty at the beginning of the project. So we started out with an initial load profile test. We wanted to improve that during the course of the project, and we did that by using real-life Michelin profiles from FPT Industrial, so using different vehicle types, different vehicle gross weights, different types of missions, so urban vehicles, long-haul missions, and then different types of fuel cell system, powertrain architectures and ambient conditions. Then this gave a whole range of different real-life emission profiles, or in fact load profiles, from which our colleagues at FPT Industrial were able to simulate drive cycles, extract the stack load profiles, and then the partnership collectively made a selection of 4 of those load profiles for testing. So the work then was post-processing at Bosch of these various selected load profiles for testing to be able to produce a modal LPT, incorporating then these different load profile tests from these 4 different missions by different weightings, and then produce an improved load profile test that we then applied to the MEAs in short stacks. So looking at the heavy-duty stack degradation assessment, I mentioned then we used an initial load profile test protocol, and then the improved test protocol that was developed during the course of the project. This initial protocol was used on the baseline membrane electrode assembly in a first test, and then a repeat test, so 2 sets of 1,700 hours of testing on those baseline MEAs. From the first generation of improved membrane electrode assembly, then a further load profile test on a short stack using the improved test protocol for 1,600 hours, and then using our second generation of MEA, and once again using this improved test protocol. There is a short stack running at Bosch. So far 800 hours achieved. That test is still running. Additionally, partner AVL has built also short stacks using the baseline MEA and using the generation 2 MEA. 700 hours of testing using the baseline MEA, and the final test with the AVL stack hardware, also on the Gen 2 MEA, then will come up for the end of the project. So in total, we have more than 6,500 hours of load profile test hours on these 5 different short stacks so far, and 1 other still to come, using initial load profile test protocols, and then the improved one developed during the course of the project, and also using 2 different stack hardware types. So this shows you here at the bottom a polarization curve, then comparing the baseline and then the improved generation 1 MEA. Moving on to the lifetime prediction. So at Bosch, established a lifetime prediction method. So this was using all of the information that came out of the AST and the LPT testing in initial phases of the project, that they were able to develop a parameterized aging model that we used to simulate the voltage loss and compare it with the actual voltage loss during the first 1800 hours of the LPT on the baseline MEA. So that's what's shown down here on the bottom left-hand side. You can see we have the measured voltage loss as the experimental points, and then the predicted voltage loss from the algorithm then developed at Bosch as the blue line. And when that is used then to actually predict the lifetime of those baseline MEAs, then that's the diagram on the right-hand side here. Then, in fact, this algorithm predicts that power, 17% of the power will have been lost at 30,000 hours of operation. So our target, of course, 10%. The algorithm gives 17% of loss, so it's not so bad, but it's not what we wanted to achieve either. So there's still some work to go to actually bring that up to achieve the target. On the risks, challenges, and the lessons learned, there are of course several. We put 3 of them here. Finally, the catalyst developments were not sufficiently mature to carry out and upscale and use them in the immortal MEAs. There was a lot of fundamental understanding developed on structural changes occurring in platinum alloy catalysts under electrochemical bias using large instruments, amongst other work, of course, that was carried out on these alloys. And all of that learning on those catalyst developments will be carried through into future and ongoing work on MEAs for heavy-duty vehicles, in particular into Project Highlander. Perhaps it was a risk to use a catalyst that provided performance at the expense of durability, but once again, those lessons will be carried forward into other work on heavy-duty vehicle MEAs. In the time that we had and the cost limitations, it was only possible to produce 2 MEA generations during the project lifetime, but really it would have been good. We needed a further MEA generation, MEA iteration in order to make use of the learning from the test results on Gen 2. Communication and dissemination activities. So the project has a website that you could consult there. The address is given there. Protexo has produced newsletters. We have a 3rd newsletter that's being written at the present time for the end of the project. Project brochures, presentations at different ongoing project workshops, certain amount of dissemination for publications so far, and different presentations at conferences. And this is an interesting point here that we've presented several times at the International Durability Working Group meetings with the DOE Million Miles Fuel Cell Truck Consortium. So that's up here. So this is something that we actually wrote into the project to set up this collaboration discussion working group with the Million Mile Fuel Cell Truck Consortium as part of the Mission Innovation Challenges under IC8. And in this framework, we have joint meetings every 2 months, but generally gather around 60 people around topical presentations, so on items that can be shared with this project and also other participants that connect. So typically on testing protocols, modeling, and also, of course, materials developments for heavy-duty application. And then finally, on the exploitation aspect, so several items that we've identified here as part of our exploitation plan. So these include, along with the various partners, the exploitation partners for that, but include a methodology standardization, this load profile test for heavy-duty trucks, the lifetime prediction algorithm, the use of components in next-generation heavy-duty MEA products, the database lifetime prediction tools, simulation methodology, and of course further R&D, and all of the exploitation activities and impact that you can read up there on the slide. Going right the way through from a standard methodology for the test protocols and the use in future heavy-duty stack testing, vehicle modeling methodology, and then on the further R&D side to continue the development and improvement of new MEA materials, including, as I said, but not only within the framework of the Highlander project. So with that, thank you for your attention. Thank you to the FCHJU and to the Clean Hydrogen Partnership for funding, and I'm happy to take any questions if you have them afterwards.
Thank you very much, Deborah. Also an interesting presentation, and congratulations for reaching some of the targets ahead of time, even though the the degradation still seems to elude you. But I would like to pick up, if you don't mind me, to jump right in the Q&A, because I have some questions for you. So in the interest of time, because we don't have so much left, there is one question which I think links also well to the last slide about the exploitation, where you were saying that the integration of the MEA, of the IMMORTAL MEA into the commercial products for heavy duty. And we actually have one question here which says, how long before the results of the IMMORTAL can reach commercial products? There are high hopes for the fuel cell trucks before 2030. It seems the durability of stack is a rather urgent point. So how fast can we really introduce this understanding of the degradation mechanisms so that we can develop stacks MEA which are better suited for trucks?
Right. So this is something that I didn't have time in this presentation to actually address, but a part of the work at the very beginning of the project was indeed to identify what is the main what are the main degradation mechanisms, and so from that work, I think we've been able to identify that platinum dissolution, electrochemical surface area loss is one main degradation mechanism. We actually saw, in terms of the membrane, in terms of the electrode, we saw minimal thinning. That the main degradation mechanism was the platinum dissolution and the ECSA loss. And in that sense, then we identified really where the work needs to be done. This is what we saw from the accelerated stress testing, what we saw from the LPT testing. We also know which stressors are the most aggravating in terms of exacerbating that particular degradation mechanism. So I think we know what to address in the next stage of work, and that's what we're doing, of course, in Highlander, amongst other activities.
Okay, perfect. But just a follow-up question, do you see then therefore a gap, still additional needs for funding in this area in order to push all of these, let's say, innovation and improvements into commercial products?
I think
would be the timeline that you imagine? Yeah.
Okay. So I mean, so ultimately, of course, we have in that baseline MEA, then we had 17% power loss by over the 30,000 hours. It's obviously not satisfactory. What is the timeline until we actually have a product in the market? Is probably 5 years or so, because what we need to do is actually further increase the performance. We need to further improve the efficiency. So we have to improve the performance at the 0.675 volt operation point, their target point, and we ultimately have to largely improve the durability. So once we have those two factors together, of course, then it's ready. I think the manufacture, the scale up. I think we've been addressing those in parallel during the course of various projects.
Indeed.
So that that side of thing is perhaps not so much of an issue, but the durability is the problem that we need to tackle. And so yes, we need further funding in order to be able to address that. Probably beyond what's ongoing at the present time.
Perfect. Thank you very much, Deborah. Let's see if I manage to come back to you for some additional question that we have here. I would like now to jump to the SHAPED project. Eric, if you're here still with us, there is a couple of questions that are addressed to you. So I would like to start with one that is being suggested by Jörg. What is the status of certification in the SHAPED project?
So we have not started the certification process. It's not part of the SHAPE project. We are working for the time being on separated tests, meaning burst test, cycling test. So we did the cycling test at vessel level, Burst tests have been done also at vessel level and were okay. So burst and cycling are okay, but we are now focusing on some other tests, which are permeation tests and fire tests. Drop will come beginning of 24 also, but so we are not working by following the complete sequence, so hydraulic leg or pneumatic leg of the Air 134, but we are working step by step, in fact, by checking individual tests one by one.
Okay, perfect. Thank you, Eric. And if you allow me, there is yet another question which is addressed to you, and it goes like this. One of the critical problems related to the tanks in general has been the cost increase of carbon fibers as a raw material. How has this impacted the project?
So that's absolutely true. We can see it in the gravimetric ratio that I show in one slide, with a gravimetric ratio of 4.8% at vessel level, which is not, I will say, the best in class. Best in class, to give you I would say a rough idea, is around 7% today for gravimetric ratio. And gravimetric ratio is the quantity of hydrogen in kilogram divided by the weight of the vessel, so meaning mainly carbon. And so not only, but mainly carbon. So this gravimetric efficiency, 4.8, is not so good versus, I will say, a spherical or a big diameter vessel. So how to answer? Are we best in class for this kind of shape? No. We have defined that the diameter of 140 that was initially defined in the project is really too small, I would say, to fly on a cost viewpoint, and on in regards to the gravimetric efficiency, we need to embed more hydrogen into one cylinder, meaning we have to increase the diameter. So the recommendation today is going from shape project is to enlarge this dimension. 140 is not enough. I think that 180 millimeter will be the ideal, I would say, dimension for the cylinders to improve the carbon fiber usage.
Understood. Perfect. Thank you very much, Eric. Sorry if I jump immediately to another question. I'm trying to get as many answers as we can. This, I think, Joël, it's for you. If you are still here with us. Yes, I see you there on screen. So we know that the project Gaia has achieved the power density target at MEA of 1.8 volt per square centimeters under certain operating conditions. Have you tried to operate the Dolphin cell under the same condition?
Yeah, yes, this is what I've shown in one of the last results with a 6-cell stack. We have used the same operating conditions, which were at a little bit higher pressure and stoichiometry. And then with we have reached 1.86 watt per centimeter square at 3 amps. Mainly by improving the flow field design, etc. A little bit the MEA, but mainly by the flow field design. So we are nearly in the same range, but we have more focus on the fuel field improvements, and maybe Deborah could confirm that Gaia has more focus on the MEA development. So really what would make sense would be to combine the two improvements of each project and see how far we could go in terms of performance increase. I don't know whether it would be possible in terms of confidentiality, but if we combine the improvements of Dolphin to the ones of Gaia, maybe we could even more increase the performance of a stack. But yes, we are in the same range.
Okay, thank you. And actually, what you said fits well with the last question I wanted to put to both you, Deborah, and Patrick. Which some of the projects that presented this morning would probably benefit from talking to each other. Is there an exchange of information? I think that you already partially answered the question, but I don't know if there are some further information that you can share with us. Are there exchanges happening between DOLPHIN, IMMORTAL, and CAMELOT?
Patrick, you're going to take that one?
Yeah, sure. I mean, I think we've definitely been in contact both with Deborah and Joël, so we're aware of the various EU fuel cell projects that are going on. I think there's good collaboration there, especially towards the annual work plan, the future annual work plan, and developing new targets and future collaboration to bring all these developments, right, and this progress that you're seeing at the MEA level and at the short stack level together.
Okay, okay, it's perfect.
I mean, I could, just come in and say that just to respond to Joel and say yes, indeed there weren't any bipolar plate flow field developments in Gaia, so the development there was indeed on the MEA. So in that sense, the two projects have a good degree of complementarity. And yes, I mean, there is communication between projects. There's I suppose, up to a certain extent, because the developments are confidential in particular to the industrial partners to a large extent. But when it's ready for communication, then they're communicated. But yeah, I mean, each of the projects as well has workshops, and these are always the opportunity as well to exchange top level information.
Perfect. Thank you very much. And I know that this is quite a strong tradition among our projects. Also in the past, we have seen common workshops, and the flow of information from the different consortia, it has never been quite an issue. When it's possible, it's always done in the interest of the whole sector. And with that, I would like to thank all of you once again, Deborah, Eric, Joël, and Patrick, for participating, for sharing with us the interest activities that you are carrying out in your projects. It's reassuring to see that we are achieving more and more results that will contribute to the next generation of the products that then can be fit into the different transport applications. So thank you once again, and I'm looking forward to meet also some of you probably at the Hydrogen Week next week here in Brussels. And I would like also to thank to all the participants that followed us until now. And now I think that it's time for a lunch break before we continue with some more sessions this afternoon. Thank you very much for your attention, and see you soon.